I'll be the chair for today's first session. I would like to first introduce our first speaker of today, Professor Chiara Mingarelli. She completed her bachelor's degree in mathematics and physics from Carleton University in Canada in 2006, then moved to University of Bologna for a master's degree in astrophysics in 2009. She earned her PhD at the University of Birmingham in 2014, where her thesis was selected by Springer Nature as an outstanding PhD thesis. After 2 postdoctoral positions as a Marie Curie International Outgoing Fellow at Caltech and Max Planck, and Flatiron Fellow at Center for Computational Astrophysics, she is now a professor at Yale. Professor Mingarelli will talk about pulsar timing arrays. Please take it away.
Thank you. Thank you so much for the kind introduction. I'm so happy to be here. I don't know a lot of you personally, and it's my first time at the Black Hole Initiative, so I'm very much in the wild, and it's really fun. So please feel free to ask me lots of questions. So today I'm going to get started with an overview of the gravitational wave spectrum, and I'll tell you how pulsar timing arrays work. Some of you might have only heard of nanograv and other pulsar timing array experiments last June. I'm going to walk you through why we think the nanograv experiment is so exciting and why we're at the beginning of a completely new field. So for those of you who are experts, I used to show this graphic saying, like estimating when we would detect the gravitational wave background, because every few years we'd come out with a new upper limit on what the background could be. And some people started to get tired of upper limits. So I would try to walk them through when we would expect to find different things. So now I can finally say that it's +0 years that we have evidence for the background. And now we get to the more interesting things, right? This was like finding the monopole of the cosmic microwave background. And now we're going to look for the individual sources and for anisotropy in the background. And then Lisa will fly maybe in the 2030s. We'll see. OK, so just to give you an overview of the landscape. At very high gravitational wave frequencies, you have the LIGO experiment. So here on the x-axis, these are gravitational wave frequencies. And on the y-axis is the characteristic strain. The characteristic strain is the sum of all of the strains from a particular source at a particular frequency. And so these lines are the detector noise curves. So here, up at 100 hertz, we have LIGO. And for someone that thinks about nanohertz, LIGO is incredible because it's at 100 hertz. So if you could hear these gravitational wave sources, they're in the human audible band. So that's why sometimes we say that chirps sound like oh. Whereas at these very low frequencies, this is more like where we have a stochastic background, and here stochastic means random. And so a random gravitational wave background is a superposition of all of these low frequency signals. So that's more like chanting at the end of your yoga class, right? That's like things are very mono frequency and don't evolve. So the sources that we detect here at very low frequencies in the pulsar timing array band are supermassive black holes. And these are the really big supermassive black holes. These are 10 to the 8 to 10 to the 9 solar masses. So in the LISA band, you would see more like the baby supermassive black holes, like Sagittarius A star. I love Sagittarius A star for EHT folks, no shade. But actually, over here in the LISA band, that's where Sagittarius A star might merge with the supermassive black hole in Andromeda, for example. So they would be in millihertz frequencies and not quite low frequency enough to be detected by pulsar timing arrays. So here we have 10 to the 8 to 10 to the 9 solar mass black holes that are merging and forming this stochastic gravitational wave background. I want to also mention that these detectors, that's okay, are, I'm rogue today, that these detectors are all complementary with very few exceptions. The experts will know the exception, and I'm not going to go into it to confuse anyone. But at very low frequencies, the innermost stable circular orbit of these black holes is around 10 to the -6 hertz, which is between these two detectors, right? And so these supermassive black holes will in-spiral, and that in-spiral will spend about 25 million years in these gravitational wave detectors. These are not transient sources. These are going to exist for a very, very long time. And it makes nanograv and these pulsar timing array experiments much more like a cosmic microwave background experiment where you integrate the signal and it gets better and better, and you can better characterize the background over time. It's much more similar to that than it is to LIGO or to LISA. Of course, all of these gravitational wave experiments measure strain. And strain is the currency of gravitational wave detectors. So it's a change in distance over distance, or a change in time over time. And so for pulsar timing arrays, we like to use time over time because it's a much more intuitive way of thinking about it. So for a strain of 10 to the minus 15, that's about 100 nanoseconds over a decade, right? That's a very small change in time over time. Whereas for something like LIGO, they have this great catchphrase, really good PR people at LIGO, that it's the change of the size of a fraction of a proton. They don't usually say over their detector arm, but they should, but maybe that's complicated. For pulsar timing, we came up with a similar thing. It's the size of a virus over the diameter of the Earth, right? Which is still kind of like a mind-blowing thing. But anyhow, 100 nanoseconds over a decade is much more reasonable. All right. Importantly, I think I don't have to say this anymore, but this was the #1 question that I got, I don't know, maybe 10 years ago when I first started giving talks on gravitational waves. People asked, well, if I look at this axis, I have very strong gravitational waves here, the strongest, potentially in the whole universe at these low frequencies. So why can't I detect them with LIGO? They're screaming loud. Why can't I see them here? And of course, the answer is that LIGO can't see these very low gravitational wave frequencies. These are just like electromagnetic telescopes. Each one of these telescopes is set up to detect a certain frequency or wavelength. So LIGO is at these very high frequencies, short wavelengths, and then here you have gravitational waves that are light years long, right? So they're just completely different detectors, and they're built to detect different sources. So our sources are supermassive black holes in the centers of galaxies. How does it play? No. They checked it right before we started. Space bar, no space bar. Click? No click. Okay. Imagine this beautiful animation where I have supermassive black holes in the centers of both galaxies. And when galaxies merge, their supermassive black holes start slowly inspiraling. Each supermassive black hole is 10 to the 8 to 10 to the 9 solar masses. And by the time they're separated by about a milliparsec, which is about the distance from the Earth to Pluto, they start emitting these very low-frequency gravitational waves. And these gravitational waves are emitted in all directions. There's a space-time fabric coming out of this animation on all sides. And some of them make their way towards the Earth, where we're timing millisecond pulsars. Now, these pulsars are neutron stars. They have their spin axis misaligned with their magnetic field lines. And so as they spin around, they send flashes of radio waves towards the Earth. Now, these flashes are advanced or delayed by gravitational waves because they change the proper distances between objects. And so as a gravitational wave that you're now seeing very clearly, like this, is transiting, help me out, Shep, come here. Please, come and help me. I need audience participation.
Okay.
You're the pulsar, and I'm the Earth.
Okay,
so it stretches and squashes space-time, right?
we go.
Exactly, like this. Like that, exactly. Thank you. And then the signals arrive early when we're closer, and then later when we're further away. But if you see us doing this dance, that could be anything. That could be a random presenter. But if you see it in 68 pulsars and all the pulsars that we're timing, then maybe something else is washing over the galaxy, changing the distances between the Earth and the pulsars. That was much better than my animation. Thank you so much. All right, so the primary source of gravitational waves in our frequency band are supermassive black holes that are slowly inspiraling. And it's our primary target of the background. And we made this really nice animation which kind of gives you the feeling of what a gravitational wave background would look like. We think that at the lowest frequencies, there's hundreds of thousands, potentially up to 1 million, of simultaneously inspiraling supermassive black holes. And these create the gravitational wave background. But there's more. There could be other things that are emitting nanohertz gravitational waves. There could be quantum fluctuations from the early universe that were emitting gravitational waves that have now been blown up to the size of the whole universe and are unfreezing from their various horizons at different frequencies. Some of them might be in the pulsar timing array band. There can be ekparodic theories of cosmology where we're bouncing and collapsing, and those could create a blue tensor index, and that could also create a signal that we might have already seen. But importantly, the way that we go after the gravitational wave signals is completely general. It doesn't matter what's making the gravitational wave signal. Our detector responds in the same way. It responds to low-frequency gravitational waves. And so the way that we actually go after the signals is by doing a cross-correlation search. And so this is one of the only equations that I'll show, and this is kind of blasphemy for astronomers. But given the fact that I sat through some quantum gravity talks, I feel like this is okay. So I have the cross-power spectral density here between pulsar A and pulsar B. And all this means is that I have, two time series of data from pulsar A and from pulsar B. And I want to see what signal is common in both of these pulsars. There should be nothing common except for a gravitational wave signal, because the noise is different in each one of these pulsars, right? They're all going to have their own weird quirks that are happening, but the gravitational wave background is washing over the whole galaxy. That signal is the same. And so by doing this cross-correlation search, I'm asking, what is the signal that's in both of these pulsars? And so I go to one pulsar and I say, okay, I timed you for 30 minutes at Arecibo on June 12th, and then this is my time of arrival stamp. And then I go back 2 weeks later and I get another time of arrival stamp. And then I go back again and I have all of these different stamps where I timed a pulsar and I know when it arrived. And then I do the same thing for all 68 pulsars in nanograv. And then I cross-correlate the signals looking for what's the same. And that should be the gravitational wave background. The gravitational wave background itself is composed of these two pieces. This piece here is called the characteristic strain. That's what was on the y-axis in the first figure that I showed you. This gives you the amplitude of the gravitational wave background. And Stirl-Finney wrote down a really nice, simple derivation of this in 2001. As a little story, I asked Stirl why he never published this, because this is a kind of famous archive paper with hundreds, if not over 1,000 citations. And he said that when he got the referee report, it wasn't extensive enough for him to bother changing the version on the archive, so he ignored it and just left it on the archive. So this is one of the most famous archive papers around in our field, and also doesn't make me feel so bad when I have an archive paper that just kind of sits there, but I'm not Stirl. Okay, so this gives you the amplitude of the background, and then this part here is a really interesting geometric term. It's called the Hellings and Downs curve if we assume that the gravitational wave background is isotropic. And to first order, it should be isotropic. Our sources are coming from very high redshift. It should be more or less the same in all directions. We can go into a refinement of that a little bit later. But what is the Hellings and Downs curve? It tells you what the correlation is between pulsar pairs that are separated at different angles. So if I have a pulsar pair that's separated by 20 degrees on the sky, I should have a positive correlation between them. And a positive correlation means that the residuals are arriving and being delayed in sync, like this, right? The pulsars are bobbing together in this gravitational wave sea. And if they're also separated by, 180 degrees, that's pi for the quantum theory people, then they're also correlated. The signals are also arriving in sync. However, if you get to correlations that are around something between like 70 and 120 degrees on the sky, then they're anti-correlated. So one signal will arrive earlier than the other one. And the level of this correlation is characterized by the y-axis. And here again, you have the angle between the pulsars on the x-axis. In the limit of having an infinite number of pulsars, you can derive this blue line, which is the Hellings and Downs curve. So why is this important? Well, if you were to just see something that's correlated between all of the pulsars, there's a lot of stuff between us and pulsars that are thousands of light years away. There's the interstellar medium. There's weird things happening at pulsars with physics that we don't really understand. So how can you be sure that what you're seeing is a gravitational wave signal? Well, the Hellings and Downs curve is our smoking gun for the background because it introduces this quadrupolar-like correlation between the pulsar pulses, right? So they're positively correlated, zero, anti-correlated, positively correlated again. Now, the experts will say this is not a pure quadrupole. If it were, it would go back up there. You are right. There are other components, and we can talk about that in the questions if you're interested. All right. So why are we so excited about the 15-year data? Well, we made a measurement here of the Hellings and Downs curve. So the blue lines are what we measured, and the dots give you the median values, and these are the 1 sigma error bars. The black line is the Hellings and Downs curve. This is what we would expect. And if there were no gravitational wave background, it would be this red line here. So we made something between a 3 to 4 sigma detection. Well, I'm not allowed to say that. Evidence for the gravitational wave background. And for those of you who aren't used to thinking in sigmas, this is a false alarm probability of something like 3 times 10 to the minus 3. Or what that means is that if I had 1,000 universes, in 3 of them, I would just randomly get a Hellings and Downs curve. 5 sigma is really the standard for saying detection, and we think that we'll get there by combining more and more pulsar data sets with our colleagues, like in Australia and in Europe. So to make this curve, we had to bin 2,211 pulsar pairs. There are 21 new pulsars with respect to our previous data release, and there are 67 pulsars that have timelines that are greater than 3 years. The Bayes factor for this evidence for the background is 900, which for those of you who like Bayes factors is pretty good. For those of you who like the sigmas, then 3 sigma is interesting, but you're not, you're going to still wait a little bit longer to get really, really excited. But we're excited. So what can this tell us? Well, in the Finney formalism, when you have a gravitational wave background that's just driven by the in-spiral of supermassive black holes, it should scale as frequency to the minus 2/3 like this, right? So what we found, and I'll show you afterwards, is a slight deviation from this. So it kind of looks like this blue line. So if nothing other than gravitational waves is affecting your black holes, it's a straight line or a power law. And those of you who do astronomy or astrophysics know that astronomers love power laws. So here, in the blue line, this is what happens if something other than gravitational waves is driving your binaries to merge. When your binaries are really widely separated, lots of things can affect them. There can be gas, there can be dust, there can be other things that are much more effective at making your binaries merge than just gravitational waves. And that effectiveness means that they don't spend as much time at these very low frequencies as they would if they were just emitting gravitational waves. And that depletes your signal, right? So this means that they're being pushed through this gravitational wave band by other physics until there's a diminishing point of return at around 10 nanohertz, and then only gravitational waves drive them to merge. And so seeing a deviation from the black line is really interesting. And so this is the first slightly more complicated result that I'll show you from the Nanograv 15-year data. And we're going to focus on this side over here. And so if I just were to just have this f to the minus 2/3 power law that Searle derived in 2001, it would be this black line. But the best fit model has it turn over a little bit at these very low frequencies. And so this could be the first evidence that what we talked about yesterday, the final parsec problem, or how the supermassive black holes eventually get to the gravitational wave emission regime and merge, is being solved by other kinds of astrophysics, like gas and stars interacting with the binary. And that's really exciting. And so now that we have evidence for the gravitational wave background, we can go beyond this f to minus 2/3 model that Searle proposed in 2001. We can say, well, if we have a realistic population of binaries, what actually happens is that you have a very slow buildup of these binaries at low frequencies. And as you go to higher and higher frequencies, the stochasticity of the background breaks down. Your black holes start to merge, and you get less of a signal at these very high frequencies. Now, high frequencies is close to 100 nanohertz, right? So just to give you a sense of scale here. And so at these high frequencies, there's very little contribution from the gravitational wave background. And this might be the key place where we want to look for the individual in-spiraling supermassive black holes. You no longer have a screaming loud gravitational wave background that you're trying to pick out the individual sources from. This background is very low, and so maybe this is where we'll find the individual binaries. Now, to find them, it's much better to look at individual galaxies. And so the reason that I'm really keen on doing targeted searches for supermassive black hole binaries is that on the data analysis side, if you do a targeted search for binaries, you can do 10 times better than if you were to do an all-sky or blind search. And today, my student, Andrew Casey Clyde, his paper appeared on the archive, the number is down here if you're interested, that showed that quasars are 7 times more likely to host supermassive black hole binary systems. So knowing the sky location and knowing a gravitational wave frequency sets you up to do a factor of 10 times better in the strain. And knowing the frequency can come from something like the Catalina Real-Time Transient Survey, for example, or any kind of AGN that has these periodic light curves. So we're really keen on doing targeted searches. We're doing them right now. My whole group is working on this. And if there's any justice in the universe, we should find at least 2 of them by the end of the decade. And these can induce anisotropy in the gravitational wave background. And so what does that look like? Well, we started with the monopole at the beginning of this animation. And as time goes on, we'll be able to better and better resolve the gravitational wave background. And so it looks blurry first. That's the first thing that we find. That's the first thing that we expect to find. But as time goes on, we'll be able to get better and better angular resolution and make these maps of the gravitational wave background. And we can borrow methods from the cosmic microwave background analysis to also look at the angular power spectrum of the gravitational wave skies. So here's an example from a paper that I wrote in 2017, where I took a realization of the local universe from the 2-micron all-sky survey and created a gravitational wave background out of it. This one has a screaming loud source in the middle, and this is what its angular power spectrum looks like here in blue with that loud source. And then if you remove it, you get something that looks a lot more like a CMB-style map. And that's what you would expect to see. And what I predicted here is that the overall level of anisotropy in the background should be around 20% of the monopole. All right, so that was a whirlwind tour, and I had a lovely guest help me with my animation. Thank you very much. I just want to summarize by saying that we've observed the gravitational wave background, and if it genuinely comes from supermassive black hole binaries, which are really the likeliest sources, we know that supermassive black holes binaries merge. There's evidence not only in the nanograv data, but also in the European pulsar timing array data and the Parkes pulsar timing array data from Australia. There's varying degrees of confidence in those evidences. However, they will improve as the square root of time and as the number of pulsars. So what's next? We think that we'll find some local, nearby, low-frequency gravitational wave sources. These can induce anisotropy in the gravitational wave background. And then in the 2030s, LISA will fly, and we'll be able to see the actual final merger of these lower mass supermassive black holes. So what's next is everything. Thank you for your attention.
Okay, we'll take some questions. I think Ramesh.
So, you talked about this gold standard phi sigma, right? Phi sigma detection of the background.
Yeah.
You're close.
Yeah.
So clearly one route is to just, nanograph given enough time will do it.
Yes.
So I have a 2-part question. The first part question is, if all you had was nanograph, how many more years do you need to reach the phi sigma?
Yeah.
But the second part, I think you hinted that already if you could just combine the data from all the different timing arrays, not just the US, then am I right that you can already reach 5 sigma? And is it only politics that's stopping you?
State secrets.
Yeah, please, yeah. Okay. We're all friends here.
Oh, yeah, of course. I'm happy to answer as best I can. Okay, I'll do it in reverse order. So yes, the International Pulsar Timing Array is doing a data combination right now between the European data, the Parkes Pulsar Timing Array, that's been, and the European Pulsar Timing Array, which now has Indian Pulsar Timing Array data in it from GMRT. And what we've finalized internally is something called early DR3. It's our early third data release. So we took all of we call them monster pulsars, the very badly behaved, difficult ones, and combined them first. to see what the answer was if we just limited ourselves to 21 of our best pulsars. And that's already interesting. We're going to have about 100 pulsars, and we're thinking of combining near-time pulsars. So the Ricarte telescope is a new SK Pathfinder telescope in South Africa, so that's really exciting too. So that is very much in development, and I would be very surprised if we didn't do significantly better than any one data set alone. Okay, so...
When will that come out? When will we see?
I think, well, so now this comes with no guarantees, right? So this is one of these big international collaboration problems, and it's motivating people to do this work on top of all of their other work that they're actually paid for. So I think it might be another 6 months to a year. But I also think it's results driven. So there's some really exciting things that are happening in all of the different pulsar timing arrays. And I think what's really going to get people moving is the first evidence for individual binaries. So if nanograv sees something at some high frequency and we get really excited about it, then we'll share that result with our international partners, and they're going to want to check their data. And then after they check their data, they're going to want to check the combined data, right, to see if the signal is still there. So I think that it's really going to go a lot faster once people are really excited. Yeah, thank you.
Yeah, so my question is a little bit related to Ramesh's, but first I'll just say I charge by the dance step.
Oh,
so you'll
okay.
get my bill later.
I'm not sure I can afford you. I should have checked.
Yeah, you should have invoiced me earlier.
Okay. As long as there's no alcohol on the bill, I can pay.
Yeah. So Arecibo is kind of off the map, unfortunately.
Yeah.
FAST it now exists.
Yeah.
So I'm trying to understand, do you do better by getting more pulsars? Mm-hmm. Do you do better by increasing the time span? And will these new telescopes make a huge difference? Does Arecibo, the lack of Arecibo, going to hurt you? What's the landscape in terms of facilities? And
that's a great question. So with the International Pulsar Timing Array, we have 8 telescopes, and they're 8 of some of the best radio telescopes in the world. Losing Arecibo was a huge loss for so many reasons. Geopolitical reasons, the infrastructure that's still there that was just kind of crumbling. So FAST can see all pulsars that Arecibo could see, with the exception of 3 or 4 of them. And so Arecibo was more important for the very high precision pulsar timing. It could get you really, really tight residuals on a pulsar arrival time. And that's more important for looking for the individual sources than looking for the gravitational wave background. So Arecibo was crucial in making the nanograph 15-year data. But we actually have 20 years of data now. So we're already in the post-Arecibo era. What we did with the Arecibo time is that we offloaded as much as we could onto the Green Bank telescope. And now CHIME in Canada is starting to do the very low-frequency pulsar timing. And we've also got VLA data. So we're supplementing Arecibo that way. But FAST is going to be really important for making the very good TOAs that we need, or time of arrivals that we need, to find the individual sources. And so that, together with Meerkat, are going to be really important for that next level of background searches and for the continuous waves.
Well, yeah, my question was along the same lines. I think the Chinese try to scoop you with a much higher sigma.
Who told you that?
Okay, and they started collecting data much later, but FAST is much better than anything else. So you didn't mention China in the International Pulsar Timing Array. You mentioned
They're not
India.
part of the International Pulsar
Yeah, so is the
Timing
future
Array.
of PTA Chinese? Aren't they going to smoke everyone else?
Let me show you something. Okay, so FAST is awesome. And not only is it awesome, but I heard from one of my colleagues that they're building more of them, right? Yes, exactly. So China, when they do something, they mean it, and they're serious about it, and they do it fast, and they do it on time. But you can't do it. You can't make up time, right? So what?
How long until they're
at least 15 years. So, and that comes from these equations here, right? What FAST ended up finding in their data was the Hellings and Downs curve. They had enough pulsars that they could find the Hellings and Downs curve. But the characteristic strain, the gravitational wave background, the frequencies that you're sensitive to go like 1 over the total observing time. And they only had 3 years of data. And the only reason that they knew to look in the bins, the frequency bins that they looked at, and that they were confident that they'd found something, was because they already knew the answer. So we'd been working with China, trying to help them develop their facilities, giving them our data analysis pipelines, teaching them how to use them. So they were able to join us when we announced evidence for the gravitational wave background. So their 4 sigma detection was of the Hellings and Downs curve, but not of the gravitational wave background amplitude. So if they'd been on their own, they wouldn't have been able to say anything at all. So they knew that they had the right answer because we had the right answer, and the Europeans and the Australians had the right answer. So they joined us, highlighting the abilities of their telescope, which is really fantastic. And for making the first detection of continuous waves from the individual binaries, fast is also going to be really important. They're not currently part of the international collaboration because that means signing MOUs, and they're still not convinced that that's right for them, but we'll see what happens.
Is there a plan to have something in Europe or the US in 15 years? Or
yes, and Nanograv is doing. The Nanograv isn't going anywhere, right? So we have already been around for 15 years. We're on our second Physics Frontier Center round of funding from the NSF. We've had funding from the Moore Foundation to improve telescope receivers. So we're very much in the game to stay.
Okay, this will be the last question.
When you say nearby sources,
Yeah.
could you please define nearby?
Oh my goodness. So nearby, when I mean nearby, is something like 200 megaparsecs, right? So very nearby. So if you don't speak megaparsecs, 1 parsec is about 3 light years, and a megaparsec is 1 million parsecs. So if there were anything that were, in Andromeda, we would have found it. That's about 1 megaparsec away. So now we're kind of out to 10 megaparsecs and beyond. But of course, this characteristic strain depends strongly on the mass of the black holes that you're looking at. And so the more massive black holes, the more easily they are to be detected. So we can already rule out the existence of a 10 to the 10 solar mass binary out to a redshift of about 0.8, which is pretty far. So we really win in terms of mass. The more massive the black holes, the easier they are to find. So much easier than scaling the distance. So we can start to rule out, if you're into black hole mass functions, we can start to rule out the very high end in terms of binaries. Yeah.
Okay, let's thank our speaker again. And the second speaker today is Dr. Anna Raclariu. She received her bachelor's degree in University of Cambridge and completed her PhD here at Harvard University in 2020 under the supervision of Professor Andy Strominger. She was a Stephen Hawking postdoctoral fellow at the Perimeter Institute for Theoretical Physics and a Heising-Simons and MCSA postdoctoral fellow at the University of Amsterdam before joining King's College. Dr. Raclariu will be talking about entanglement, self-modes, and infrared on-shell action in asymptotic flat spacetimes. The floor is yours.
Thank you very much. I think I should use the microphone that I have attached. Okay, thank you. Thank you very much for the very nice introduction. It's always great to be back here at the BHI. So today I'm going to be talking about some work that I've done with Vincent Chen and Rob Myers, who used to be at Perimeter Institute. So now Vincent is a postdoc at UCSB. As well as Temple He and Catherine Zurek from Caltech. So the context for my talk are asymptotically flat spacetimes. So these are solutions to Einstein's equations with vanishing cosmological constant. And these are spacetimes that are really far away from events or sources of interest, look like Minkowski space, so like flat space. And they are compactly depicted on this diagram here, on this diamond. So the key property of these so-called Penrose diagrams or conformal diagrams is that they preserve the causal structure of space-time. And so one of the distinguishing features of asymptotically flat spacetimes is the fact that the boundary, that appears at infinity, is a null surface. And also in orange here, you can see a time slice through the spacetime. So moving along this way is like going to larger and larger distances, and we also have time going upwards. Now, these are relevant if you are interested in physical questions that, for example, would involve scattering. So the simplest example of an asymptotically flat spacetime is just Minkowski space. And of course, that will enter if you, so this would be a fixed background, and this would enter if you're interested in basically scattering particles like you would do at the LHC at very high energies below the black hole formation threshold. So if you form a black hole, then the spacetime is going to be distorted, and other things may happen. Interestingly, related to black holes, and I've heard a beautiful talk just this morning, you can also use scattering to describe gravitational processes such as black hole mergers. So in this case, you can approximate a black hole by a massless particle. So these particles would again come in from infinity. They would sort of like approach one another. They would spiral in, and in the process, they would be emitting gravitational radiation that would then move on and go off to the boundary, in this case, to future null infinity. Now, the physical observables in such scattering processes are scattering amplitudes. The scattering amplitudes are basically overlaps between incoming momentum eigenstates and outgoing momentum eigenstates. And their overlaps basically define, and the scattering amplitude is basically an overlap between these states. And there is a unitary, we believe, a unitary evolution operator that relates these states. That is called the S matrix. Now, these S matrices are, and scattering amplitudes in particular, are in general very hard to calculate. However, we are very lucky that in quite general situations, they are constrained by symmetries, and the symmetries are generated by non-trivial charges. And we have heard a beautiful talk by Mina just at the beginning of this conference about this. So the idea here would be that this charge conservation law would translate into a commutation relation with the S matrix. So you can think about the S matrix as evolving in time, and symmetries these charges would be preserved under time evolution, and hence would commute with the S matrix. So one can write down the conservation law in this particular way. Now, what turns out to be the case, and this was shown by Andy and collaborators about 10 years ago, is that these Ward identities are actually associated, they are exactly equivalent to so-called soft theorems. So these are universal relationships between amplitudes that include low energy radiation and amplitudes without such low energy radiation. Now, what are the symmetries that I'm talking about? So in gravity, so these symmetries exist in both gauge theories and gravity, in any theory with massless particles. In gravity, they include so-called supertranslations. So these are angle-dependent translations. And on these diagrams, you can think about them as shifting points on cross-sections of these null cones independently by different amounts. And these symmetries were already discovered quite a long time ago by Bondi, van der Burg, Metzner, and Sachs. And the conservation law associated with these guys leads to the leading soft graviton theorems. Now, there are also, and these were discovered more recently, angle-dependent Lorentz transformations. So these are transformations that now preserve these spheres but shift points, again, depending on the angle that you are at while preserving these spheres. And quite remarkably, again, through the connection to soft theorems, and in this case, the subleading soft graviton theorems, it was shown that these, the algebra together, the symmetry, the algebra of the symmetries is actually the same algebra that appears in two-dimensional, in a two-dimensional conformal field theory. So this is the so-called Virasoro algebra. And using this nice, perhaps coincidence at the time, later on, just a few years ago, it was shown, so using methods from 2D conformal field theory, it was shown that there in fact exists an infinite a whole tower of other symmetries that involve higher spin generators, and in fact, an infinity of such higher spin generators. And all of these, so physically, all of these generators are related to increasingly subleading modes of a graviton in an energy expansion, in a low energy expansion. And another way to say it is that the generators for these higher spin symmetries can be associated with higher multiple moments of the gravitational field. So they are present in gravitational radiation. Now, this was all about scattering, but you can imagine that asymptotically flat spacetimes are also relevant if you're trying to understand the near horizon physics. So an example where horizons appear are just, again, in just flat space, where you consider a subregion and its causal development. Another example where such causal diamonds appear are in the region exterior to a, say, Schwarzschild black hole on one of the two sides, as well as perhaps in other spacetimes with other cosmological constants, such as anti-de Sitter or de Sitter space. So here I'm showing the static patch in de Sitter space, and again, we have a horizon. Now, universal physics, we believe that there's quite some evidence that universal physics is captured by quantum field theory with a high degree of symmetry, or conformal field theory that lives in a lower number of dimensions. And we may expect this. So we have examples, many examples of this through the ADS-CFT correspondence, and we've heard beautiful talks by Julia and Alex and so on about these kind of correspondence. But we may expect this to also be true in other backgrounds, so in particular in asymptotically flat spacetimes. And through this relation with symmetries that I just presented, we expect that the theory of gravity in 3+1 dimensional asymptotically flat spacetimes to be in some sense described by a conformal field theory that lives in two lower number of dimensions. So in this case, in 2 dimensions. So this is motivated by this connection, by this appearance of these Virasoro symmetries that I briefly described before. Now, the outline of my talk is going to be as follows. So first, I'm going to, so I'm mostly going to focus on the second part of questions that I described, namely questions that have to do with horizons and subregions in space-time. So first, I'm going to focus on Maxwell theory, and we'll see that there are structures in the infrared of these theories that are universal, and we'll see that they are similar to those appearing in gravity, and we're going to look at how to characterize subregions in such simple theories, and how basically these symmetries, this infinity of symmetries that will be present in this context, as I will describe, actually lead to constraints and hence non-trivial contributions to the entanglement entropy across a particular subregion. And then in the second part, I'm going to move on to gravity, and I'm going to discuss a simple example, so a toy model of gravity in asymptotically flat spacetime, where I will show that one can actually define an on-shell action that is non-trivial despite being in asymptotically flat spacetimes, as we will see, which mimics this relationship that we are very familiar with from ADS holography, namely that the bulk partition function with certain boundary conditions acts like the generating function of correlation functions in a 2-dimensional conformal field theory with sources that are given by the boundary values of this field. So to start, I'm going to be considering 4-dimensional Maxwell theory in the vacuum, so with no charged particles. In these theories, one can define an infinity of large gauge charges that are given by integrals of the electric field around some sphere at infinity, weighted by a function on the sphere. Now, you may be very familiar with the case where this function on the sphere is actually a constant, in which case These charges would be just the global charges in Maxwell theory. But of course, here we are in the vacuum. We don't have any charged particles. So in that case, we'd expect these charges to vanish. And indeed, one can show that that is the case. And to see that, one uses the constraint equation at Scri plus that relates basically different components of the electric field. So this FRU component is, roughly speaking, the radial electric field, and this FUZ component are the radiative modes. And so we have this relation. This integral can then be written as an integral of the radial electric field, so of this FRU component on the sphere. And then one can use the constraint equation to replace this component of the radial electric field by these radiative modes. And then basically this formula just becomes this other formula that now relates, that now is given in terms of the change in the gauge potential across future null infinity. So again, in a particular gauge, the change in the gauge potential is basically given by the integral of this radiative electric field and is in general non-zero. So its modes, since it's a total derivative on the sphere, what appears here would be 0 in the case where epsilon is equal to a constant. So this confirms what we advertised, that the global charges vanish in vacuum. However, it's non-zero in general for arbitrary functions on the sphere. So if you are looking at higher moments of these charges on the sphere. And these large gauge charges are actually related to so-called the memory effect that we have heard about from Bob Wald's talk at the reception. So these are exactly, they are exactly related to the memory effect, which basically tells you that if you have electromagnetic radiation that goes off to null infinity, then that will induce a change in the gauge potential across null infinity. And hence will also turn on these large gauge charges. Okay, so how do these solutions look like that have these modes turned on? So again, from the constraint equation, we can see that we can solve this constraint with these simple field profiles. Namely, we can choose the radiative field to be a delta function in U, and we can choose the Coulomb field to be a theta function in U. And you can see by choosing an appropriate distribution on the sphere that these will, roughly speaking, you'll be able to solve these constraints with these field profiles. And I'm also showing them on these on the Penrose diagram here. So the red lines are basically these radiative modes. They propagate along the null cone, whereas the Coulomb modes propagate along null plane in spacetime. And these are solutions that carry non-trivial large gauge charges in electromagnetism. So this will be a very important point in what I'm going to say next, which is that actually the Hilbert space of these theories, when you have such charges, will organize into superselection sectors of different large gauge charge. And hence, we'll see that that will lead to a non-trivial contribution to the entanglement entropy. Now, we are interested not in the full space-time, but rather in a particular subregion in the space-time. So here you can consider the two Rindler wedges in space-time. So you can take a Cauchy slice and split it into two halves. I'm going to call the causal diamond associated to one half the left diamond, and the other one, I'm going to call it the right diamond. And the Gauss law in general will impose a constraint, namely that the charges, one can define, I'm skipping a lot of details, but one can associate these subregions also with some charges that I'm going to call Q left and Q right. And the constraint, there is a constraint that tells us that the sum of these two charges has to be equal to the large gauge charge. And hence, all physical states in this theory, they have to lie in the kernel of this entangling constraint. So the sum of the left and the right charges has to be equal to the large gauge charge. Now, a particularly simple state, in this case, is just the vacuum state, which has an associated vacuum density matrix of this form. In that case, the net large gauge charge is just 0. And the constraint tells us that the large gauge charge should commute with this density matrix. And then one can use this decomposition into left and right charges to get this equation, then trace over the left sector to end up with a relationship that tells us that the reduced density matrix in the right region commutes with the charges in the right region, which hence tells us that this density matrix decomposes into blocks of definite right charge. Now, the probability distribution that appears here is a probability distribution over these different superselection sectors that can appear, and it can be determined using path integral methods to be an exponential of some action with some normalization. What turns out to be the case is that this action is actually an on-shell action associated with the conformally soft modes that I've shown and I've described before. And these modes are precisely the modes that turn on charges in the right region. And they can be seen to be field configurations that are localized at the entangling surface or edge modes. So these were described a long time ago by Donnelly and Wall. And here we are basically just giving a different interpretation, a new physical interpretation of this older calculation. Now, here is also, just to see it, the on-shell action of these edge modes actually takes this very simple form. First of all, we see that it's localized on a two-dimensional space. So in 4 dimensions, on a codimension 2 slice. In 4-dimensional space, this would be like the entangling surface. It's a codimension 2 slice. And it's given in terms of this Q parameter, which is related to just the field strength or the charge, if you want, associated to the subregion. And one can use this action, in particular this formula, to then compute an associated entanglement entropy that will give a non-trivial contribution to the net entanglement entropy of the vacuum state in Maxwell theory. Now, I don't have that much time left, so let me just briefly sketch how to perhaps generalize these ideas in gravity. So in gravity, subregions are difficult to describe because they have diffeomorphism invariance, so it's hard to define a subregion. But let me just start by describing the full a story in the full spacetime. So I'm just considering an asymptotically flat spacetime that's given by the Minkowski metric plus perturbations that fall off as one moves away towards the boundary. And this function CZZ is so-called shear. And its if the time derivative of this function is non-zero, that means we have gravitational radiation. So here I'm going to restrict to the very simplest example of such shear profiles that are so-called soft. So there is a zero mode. I'm assuming that there is going to be a zero mode, so function of the sphere on the sphere, as well as a memory mode. So this memory mode would be like the zero mode of the gravitational radiation. So in principle, you are going to have all sorts of other modes as well, but I'm restricting to just the infrared sector, to the simplest case. And this second term here is the analog of the gravitational memory that we described before, and it turns on the associated charges in this context. So this is the leading gravitational memory, and this is just the zero mode, also sometimes known as the Goldstone mode. And the key thing is that these two modes have been shown to be canonically paired to one another. So they are variables on the gravitational phase space. Now, if you want to compute a boundary action in this context, what one does is to start with the Einstein-Hilbert action and vary it, in which case one gets a term that is proportional to the equations of motion, and another term that reduces to a boundary term that lives on the boundary. So here, the boundary, we can imagine it to be this null surface that we've seen, this boundary of the causal diamond. And now, in addition to this, one typically imposes the Dirichlet boundary condition, which means that one typically fixes the induced metric on the boundary, in which case one ends up, so this boundary contribution here with these particular boundary conditions will just be proportional to a change in the trace of the extrinsic curvature of the boundary. And so this was shown a long time ago by Gibbons and Hawking. In order to have a well-defined variational principle, one has to add a term that's proportional to an integral of the trace of the extrinsic curvature to the original action. Now, in vacuum, if you have vanishing Bondi mass, this boundary action can be shown to vanish. So on shell, this boundary action vanishes. However,
that's a bit too fast because the Dirichlet boundary condition actually turned out to kill this radiation, so to kill this flux that one can in principle have through scry. So one can ponder whether there is another set of boundary conditions that one can use in this particular case that would allow you to have a non-trivial memory mode through scry. So instead, what one can do is to start with this shear profile, which is the data that one can specify at infinity, and instead of fixing it all, to just fix this zero mode instead. And if one does that, what one ends up with is actually a non-vanishing on-shell action that is just a function of these two modes, of this memory mode and of this shear. You can find this by just plugging it into this formula. And it's quite a nice action. It looks quite similar to some other actions that have appeared in the literature before, but one thing that's not so nice about it is that it transforms non-trivially under diffeomorphisms. That can actually be remedied, as was shown in some older work by Donnelly and Friedel, through the addition of a corner term. And this corner term would again live on a codimension 2 slice, and its addition would basically ensure that this action becomes diff invariant. So one can do that, and after doing that, one obtains, I'm not really going to have time to go in details through this calculation, but basically this resulting gauge invariant boundary action turns out to coincide with sort of three quantities. If one looks at the linear order in N in this action, it turns out to be related to the soft charge in this context. It also turns out to be related to the so-called, well, I'm not sure if I should give it this name, but it's been recently discussed by Verlinde and Zurek as an effective action that they use to reproduce a funny relation between correlation functions of space-time fluctuations in gravity. So note that we'd expect these to typically be suppressed. Space-time fluctuations are expected to be of the order of the Planck length. Instead, what they found using some particular reasoning was to show that actually these fluctuations are enhanced by an infrared scale. And they used an action that one can now see to be exactly related to this boundary action obtained by on-shell calculation in the way that I have argued. And the last thing is that the same action also turns out to agree with the so-called soft effective action that was put forward by Kapets and Mitra in relation to correlation functions in this two-dimensional proposed holographic dual of gravity and asymptotically flat spacetimes shown to reproduce basically soft insertions. So I'm out of time. So to summarize, I have discussed the relationship between soft modes and their implications for basically entanglement entropy in Maxwell theory. We have seen that the soft modes turn on the soft charges that are large gauge charges associated to subregions, and hence this entanglement entropy can be thought of as due to fluctuations in these charges. And then we have discussed a little bit the problem of defining a boundary action, an on-shell action in asymptotically flat spacetimes, and showed that, well, I didn't really have time to go into the details, but argued that this boundary action has appeared in different other places before, and it's sort of universal and describes infrared physics in this context. So there's many things that you can try to ask about in the future. So one of them would be to try to understand really how to generalize this gravitational discussion to subregions. Another one would be to go beyond this leading soft sector, and another obvious one would be to try to understand the implications of all of this for black holes or de Sitter or other backgrounds or horizons more generally. Thank you.
Okay, we'll take some questions.
So if I can, like two brief questions. So in this electromagnetic story, I think I kind of missed the punchline.
Yeah.
So, yeah.
Sorry, it was a bit fast. So the punchline is that if you look at the subregion in E&M, just the vacuum, then you can have, that subregion can be associated, can have any
basically a large gauge charge. And hence, there is a non-trivial contribution to the entanglement entropy that comes from the fact that you can have these super selections of the different large gauge charges.
And then do you have a formula for that?
Yes.
I think that's what I...
Sorry about that. Yeah, so the formula is that here is a density matrix associated with the subregion that can be mapped to a path to a partition function. That partition function is basically related to this, and it's given by an integral over the super selection sectors of an exponential of this on-shell action of the soft modes, normalized in this particular way. So and then one can use that partition function together with this thermodynamic formula. It's Euclidean partition function, and then compute this entanglement entropy. You can also just use this formula and sort of do a continuum version of the standard Shannon and apply the Shannon entropy formula with this probability distribution in the continuum limit to get this edge mode entropy.
And then this final answer, is it something finite? Because it might seem like you could just write one
the
more
final
equality.
Answer, so I haven't written it down because actually the final answer has also been written down in some other in this paper by Donnelly and Wall before. Yeah. It's exactly the same answer that they got, and it has a piece that's it's a divergent contribution to the entanglement entropy, like a logarithmic contribution. Yeah.
I see. So yeah, so it has log of the area of some area of entangling surface, or just log?
Yeah, the log that appears in there is it's related to the area of the entangling surface.
Okay, thanks.
Okay, any other questions?
In the gravity case, you had a boundary.
Yeah.
And then there was suddenly a corner. Where was the corner coming from?
Yeah, sorry, I glossed over that. So the boundary, sorry, I have a picture. So we have a boundary. You'd expect to get something that lives at scry, right?
Yeah.
In this particular context. And you can compute that for this soft shear profile configuration with this boundary condition. Sorry, that you fix the Goldstone mode, so the zero mode of the shear. And so this naive calculation without any corner pieces or anything gives you this answer. But this answer is actually, of course, you have to add the contribution. This is just for scry plus. You have to add the contribution from scry minus. But each of these terms independently, when you apply a diffeomorphism, because the symplectic potential actually transforms non-trivially under diffeomorphisms, and it actually, okay, this is well known to experts, but it doesn't transform. It is you can think about it as a d-1 form in space-time, in d-dimensional space-time, but it actually doesn't transform like a d-1 form. There is an additional contribution that comes from the fact that this is a 1 form in phase space. And hence, this potential shifts. So in general, it will shift under diffeomorphisms. And it was shown using this transformation rule in this paper by Donnelly and Friedel, but potentially also like earlier. I'm not sure if they were the first ones to say that, that actually this one can get a diff invariant boundary action by adding a term that just lives on a codimension 2 slice. So here it would be, the corner in this particular case would just be the past boundary of scry plus and the future boundary of scry minus. So you'd add to that, you need to add to that something that lives on the codimension 2 slice to make a gauge invariant.
Okay, if there are no more questions, let's thank both of our speakers again, and we'll have a coffee break.
All right, welcome to the final session of the conference. My name is Angelo Ricarte. I'm a BHI fellow, and I work on how black holes interact with their environments from event horizon to cosmological scales, and I'll be the chair of the session. Our first of two speakers is Emily Liepold, an astronomer and postdoc at UC Berkeley. She's an expert in the orbital modeling techniques with which one can infer black hole masses, and may be as obsessed about the M87 galaxy as we are about its wonderful black hole. So please take it away.
Great, thank you so much. Yeah, it's great to sort of start off this last session with some very observational updates. So today I'm going to talk to you guys about recent progress that's been made in stellar dynamical measurements of ultramassive black hole masses. And I'm throwing this word ultramassive up here to really emphasize how big the ones that I'm going to be talking about today are. These are basically those above, say, 1 billion solar masses, which I think in a couple previous talks, folks said supermassive up to about 1 billion, so I guess this has to be something else. A lot of the work that I'm going to talk about is done by myself and other folks with the Berkeley Big Black Hole Bunch, which is myself, Matthew Quenneville, Jacob Palawa, and Changpei Ma. So I'm going to more or less split this talk into two sides. One is going to be very observational, how do we find supermassive black holes using stellar dynamics? And the second half is going to be very modeling based. How do we actually make the measurements of these black hole masses? So let's dive in. So to motivate things a little bit, big black holes are really intriguing objects for a number of reasons that we've heard about over the past couple days. We heard just this morning, these things are potentially sources for PTA observations. Of course, these things are potentially sources for EHT observations if they're sufficiently massive and sufficiently nearby. As the most massive black holes, they're going to be the endpoints of merger processes, evolution processes, accretion processes. So if you want to be understanding those processes, these are really constraining the very, very extreme ends. Big black holes are also just booming as a little subfield. At the moment, there are approximately 27 measurements from stellar gas dynamical methods that are above 1 billion solar masses. And there are 4 measurements that are above 10 billion solar masses. But a lot of these are very recent measurements. There are 12 of them, 12 of those 27 just from the past 3 years, and 8 of them are already just this year in the past 5 months. So we're really reaching this cool space for ultramassive black hole mass measurements where our techniques that our group uses for making these measurements are really maturing, as is the case with other groups, I guess basically our competitors, where their techniques are also maturing. So we're really excited to be in a space where over the next few years we might expect many more measurements. So one of the issues, though, is that really big black holes are kind of uncommon. So here I have the sort of standard black hole mass bulge relation. And I just marked a bunch of lines on this that are probably not especially illuminating. The point being that if you want to look at extremely massive galaxies that are expected to have extremely massive black holes, they actually get pretty sparse. We might expect only about 200 galaxies within 100 megaparsecs of us that have stellar masses above 10 to the 11.5 solar masses, which will have black holes of about 1 billion. And if we go a factor of just half a deck larger in mass, we might only expect something like 20 galaxies that'll have black holes above 3 times 10 to the billion solar masses within 100 megaparsecs of us. So this really means that even if we have a full, complete sample of these things, we still only have n equals 20, which means we want to really understand these very few objects as best as possible. Okay, so there are a bunch of techniques for finding supermassive black holes that really depend on what type of galaxy we're looking at, and especially their distance. So in exactly one case, we can trace out individual stellar orbits, looking at S2 around Sagittarius A star. For 2 galaxies, we can look at the shadows from the event horizon. For a large collection of galaxies, we can look at gas dynamics near the center, where we trace out motions of ionized or molecular gas and then work out the mass distribution from that. The main focus of today's talk is integrated stellar motion, where the restrictions are that we need to have a galaxy that has stars, which I understand is most of them, and we need to more or less be able to resolve the sphere of influence of the black hole, which is maybe a couple arc seconds, but that's very doable with instruments that exist today. If we're looking at even larger distances, you can use AGN with reverberation mapping or emission line widths to infer masses, but those still require local measurements to sort of calibrate their methods. So we're going to focus on this. So the basic idea of integrated stellar motion is not especially complicated. The idea being that if you have a relative velocity between you and a star, there's going to be a Doppler shift in the star spectrum. And if you have a distribution of relative velocities coming from a population of stars that you can't necessarily individually resolve, you'll see a distribution of Doppler shifts in the resulting spectrum. So if you can work out what that distribution is, that tells you about the motions of these stars, and you do a bunch of modeling to infer back what the mass distribution of the galaxy likely is. And hopefully then there's a supermassive black hole somewhere in there. The observational requirements for integrated stellar dynamical methods, first, of course, we need to obtain spectra. We need those spectra to be extremely high signal to noise because we want to measure the shape of these fairly shallow absorption features in the spectra. And we want to measure the shape precisely enough that we don't just have a location and a width, but basically the entire shape out to fairly large velocities. We also need both high spatial resolution and large spatial coverage so that our observations extend all the way from the region where the black hole at the center is dominating the potential all the way out to where dark matter is. And we want to do a bunch of modeling with this. Okay, so now I'm going to plug the Massive survey, which is our group in Berkeley's attempt to do this sort of at scale. So Massive is a volume and mass limited survey that looks both photometrically and spectroscopically at roughly the 100 most massive galaxies within 100 megaparsecs of us in the northern sky. We've been putting out a number of papers at this point looking at as many properties of these galaxies as we can. We've looked at the stellar populations of these galaxies. We've looked at the molecular and ionized gas kinematics. We've looked at the stellar kinematics for these galaxies. We've done a bunch of HST and CFHT photometry. And most importantly, we're now in the stage where we're really trying to churn through making a bunch of supermassive black hole mass measurements of these galaxies. And of course, there are a lot of people who have been involved with this project at various times that I'm not going to fully enumerate today. There are also other groups, of course, that are doing similar types of work that I should mention. There's the team that's at the University of Vienna that's led by Glenn van den Ven. There's the team in Leiden that's led by Jens Thomas, and there's the team in Michigan that's led by Monica Valeri. And they're all also doing fantastic work with this, in this sort of subfield. Okay, so I'm going to turn now to an example of one type of, or one sort of instance of these types of observations, and that's M87. So we looked at M87 using the Keck Cosmic Web Imager, or KCWI, across 4 observing runs from basically the start of the pandemic to April of 2022. This instrument has a fairly small field of view. It's just one of these little rectangles, but we used it in sort of a mosaic sense, building out an incredibly extensive map of the stellar kinematics of this galaxy. So in total, we can extend from this region where the black hole is dominant all the way out to the area where the dark matter halo is dominant. KCWI is an integral field unit. So more or less, it's giving us a 3-dimensional picture of this galaxy where at each of the pixels through this entire space, thousands and thousands of them, we obtain a spectrum of the stars in that region, which we can see right here. So this is just pulling out a small handful of the spectra at different radii through the galaxy. If we're looking right at the center, within about an arcsecond of the center, we have this guy at the top, and if we're 100 arcseconds out into the region where dark matter is dominant, we get something like this at the bottom. We can see that there's extremely high signal to noise everywhere, and in all of the 500 or so spatial bins that we have covering this field, we get similarly high signal to noise, roughly 150 to 200. So in these spectra, there are a number of absorption features. So there's, say, calcium H and K over here. There's magnesium B over here. And what we're going to do is perform a set of spectral fits which allow us to measure the velocity distributions that are associated with the Doppler broadening of those lines. This really tells us about the motion of stars all the way throughout M87's stellar halo. Okay, so we can do all sorts of fun things with this data. On the left side, we have the velocity map of M87, and we can see that that one side is coming towards us, the other side is moving away from us. So M87, in contrast with other, very massive elliptical galaxies, actually has this really strong sense of rotation throughout its stellar halo with an amplitude of about 30 kilometers per second. This rotation is actually misaligned with the photometric axis of this galaxy. So this is elliptical, so the isophotes of the galaxy have a long axis associated with them, and that's about 45 degrees misaligned with that sense of rotation. So this ends up being a really important feature because you actually can't obtain this kinematic feature if you have fairly simple symmetries in your stellar halo, for example, sphericity or axisymmetry. But this is consistent with a triaxial intrinsic shape to the galaxy, which is maybe a spoiler for like 10 minutes from now. Okay, and then the last thing here, we can actually also look at just the widths of these velocity distributions, like the velocity dispersion. And what we see is that as we move towards the center of the galaxy, that velocity dispersion gets extremely high, and it gets very high very quickly, which suggests that we just found a black hole. But I think we already knew that there was a black hole there, so I don't think we can say that we found it, but other people have done that. So the next objective, of course, is to model that, to figure out how massive that object is. But before that, I'm going to plug some other ongoing work that we have. So roughly this time last year, we got JWST observations of M87. This was work that was led by Janelle Walsh with co-investigators Jenny Green, myself, and Chengpei Ma. So we used NIRSpec, about 10 hours with that instrument, to obtain this really beautiful sort of image of M87. So this is the image at 2.3 microns. NIRSpec is an integral field unit, so it gives us, at each of these pixels, a spectrum. So that's what we have over on the left side here. The bottom left is the spectrum from a single 0.05 by 0.05 arcsecond spaxel in the JWST data cube. For comparison, the most recent sort of adaptive optics observation of this part of the spectrum for M87 was in Karl Geppert's 2011 paper, which produced the most recent stellar dynamical mass measurement before our work. Here we're taking all of the pixels basically within, between these two rings, and they're summing them up. And you can see that it has substantially lower signal to noise than what we're getting from just a single JW spaxel. So we're really excited about the spatial resolution that we're going to be able to obtain with this. And it really should give us stellar kinematic information all the way down to the center within the central 5 parsecs or so, which is basically the best view of M87 that anyone's ever had. But NIRSpec doesn't just look at this very narrow CO bandhead region. It runs all the way from like 1.6 microns out to about 3.2 microns. So we can do a bunch of additional science with this entire spectrum. In particular, we find that there are a bunch of these gas emission lines that, they should be there, but we find that they do in fact exist. And this will allow us to trace the kinematics of the gas near the center of M87 as well. Again, in higher spatial resolution than has basically ever been done before. This will also allow us to do simultaneous measurements of the gas and stellar kinematics, which means that we can avoid some of the systematics that have popped up in analyses of stellar and gas kinematics modeling. So we're really excited about this. And this work is very much ongoing. I was sent this data cube like a week ago. So if I wasn't here, I'd probably be like analyzing it right now. Okay, so, and another thing to plug, our collaboration has another JW program going that's similar in spirit to this, that should be observed sometime this fall. Okay, so now I'm going to move on to sort of the second half of things. How do we actually measure supermassive black holes using stellar dynamics? So there are a number of techniques that one can use that range from being very fast and cheap methods to very expensive methods. The cheapest is to just use something that's totally analytical, like use a virial theorem to just write down what the mass is. This requires lots of assumptions and approximations and maybe gets you within an order of magnitude, but it's not actually that precise. Again, we have like 20 sources that we might care about, so we really want precision. You can go a little bit further doing genes modeling, but that still has a bunch of assumptions, and it's still not incredibly precise. The most general thing you can do that also is the most precise is to use short-shield modeling or orbit modeling, where you estimate the mass distribution by integrating and superimposing hundreds of thousands of orbits. So I'm going to mention how we do that really quickly. So in short-shield modeling, basically the technique is that we first propose some potential that describes our system. That includes stars, it includes a black hole at the center, it includes a dark matter halo at the outer parts. We then integrate hundreds of thousands of representative stellar orbits that we think will populate the entire phase space of the problem. Basically, all of the orbits that can possibly exist in this galaxy are represented within this library. We then superimpose those orbits such that all of our assumptions about what the potential looks like are obtained. So this ensures that the potential and mass are self-consistent. We also superimpose them such that we can best fit some set of observations, like the kinematics that we just looked at. And then you do this over and over and over again, trying different potentials. Eventually, you can find something that looks about right. This, however, takes tens of thousands of models. And every single model is like tens of CPU hours. So the total cost for one galaxy with this is something like 100,000 CPU hours, which is a lot, but not a huge amount. It's still manageable and means that we can basically move into production mode with just a few million CPU hours in an allocation. So our group has done a lot of work to improve this technique, which I'll just sort of flash up here. I don't have a lot of time to discuss it. Just this past month, we put out a paper that was led by Jacob Plawa that was doing robustness tests with mock galaxy data. Basically, if we feed in data with a known set of parameters, we get those parameters back, which is a great validation of our technique. Okay, so we fed all of those kinematic observations of M87 that I just mentioned into our code trios, and we find a couple things. First, we find that there's a black hole mass of about 5.4 billion solar masses at the center. This is about a sigma or so lower than the EHT accepted value, which is intriguing, but not necessarily like a crisis. We also find that the interstellar mass-to-light ratio is like 8.5, and that there's a mass-to-light gradient in M87. This is consistent with observations from stellar population models of M87. We also find that the average axis ratios are like 1 to 0.85 to 0.72. So the stellar halo of M87 is a bit squashed in both of its, I guess, in each of its principal axes. The three axis lengths of the ellipsoids that describe the potential and the density all have different lengths. This is, in fact, the first determination of the shape of the stellar halo of M87, which is something we're really excited about. There was, when this paper came out, a press release that included the phrase that it's potato-shaped, and that's kind of been haunting me because I've since learned that like USDA restrictions about potato shapes actually exclude M87. So it's not potato shaped. We're gonna have to find a different vegetable. Okay, so this is what we've done with this. There's also some other cool stuff that we can do with these models. So I've thrown up here the photometric major and minor axes of M87. These are basically the long and short axes of the light distribution. As I showed a little bit ago, there's a sense of rotation at large radii that's misaligned with these. And of course, M87 has a jet, which in fact is just about perpendicular to the kinematic axis in projection. So the jet is actually pointing almost towards us. It's 17 degrees off the line of sight. But in projection here, it's just about 90 degrees off of the kinematic axis. So one of the cool things that we can do with our modeling, because we have all of this internal information about the orbital structure of the galaxy, is that we can actually write down, how are the stars moving? And we can write down the mean stellar angular momentum vector of this galaxy. And we find that over the region where it's easily measurable, low systematics, it's about 19 plus or minus 9 degrees misaligned with the jet. So, this is in 3D. So this is basically saying that we have these two vectors that are very close to each other, almost as close as they can be. And we're not entirely sure why this winds up being the case. But it's something that's intriguing to us and something that we're actively investigating and want to look into further. Because this suggests that there are a lot of these apparent alignments at many different scales in M87. In particular, the black hole spin axis is assumed to be misaligned with the jet axis. We're finding that the jet axis and the stellar angular momentum axis are fairly closely aligned, probably better aligned than you'd expect from just a random draw. And you can also look at much larger scales. If you look at the galaxies within the Virgo cluster as a whole, that has a relatively elongated elliptical shape. And that axis in 3D also happens to align fairly closely with this. So there's this fairly intriguing feature that all the way down from event horizon scale out to megaparsec scale, there's this shared axis that seems to be important. So we're intrigued by this and not entirely sure what to do with it yet, but we're actively pursuing that connection. So I'll sort of close out with some ongoing efforts and connections that we have in our work. So of course we have lots of additional massive galaxies that we still want to model. I'd mentioned that we have about 100 targets, and of those 100 targets, I think we've now reported mass measurements on 3 of them, which leaves roughly 97 to go. So keep an eye out for a couple papers that are very close to being out. One on the galaxy NGC 57 that our grad student Jacob Palawa is working on at the moment. And NGC 57 is kind of interesting because it turns out to be a fairly big black hole that's in an incredibly isolated environment, which is kind of striking and unexpected. And NGC 315, which updates the mass that had previously been made using gas dynamics. I've been working on a project of looking at ultramassive galaxies, which are galaxies that are even more massive than those in massive, which is why I guess it's called ultramassive. These are substantially more distant, out to hundreds of megaparsecs from us, and they're expected to have really, really big black hole masses that dwarf even those that we've measured in massive. So keep an eye out for Holmberg 15A, which I have a paper that's very nearly out with that. That updates the mass there, ends up being 22 billion solar masses, which is I think the second largest that we know about. I was kind of hoping it would be slightly larger so I could say it's the largest that we know about, but oh well. We're also always excited about connections with other pieces of science. Of course, what we do can inform potential continuous sources for PTA analyses. We also have a paper that's hopefully hitting archive this weekend or on Monday, sometime very soon as I bother to do it, I guess, where we compare a bunch of stellar mass distributions that we find for galaxies in the massive survey and try to infer what kind of gravitational wave strain we might expect if those black holes follow standard scaling relations. And we find that the mass distributions that we have in massive are actually consistent with the gravitational wave strain that folks like nanograv have found, which is really exciting. And of course, massive nearby supermassive black holes are always potential targets for EHT. So if we happen to find one that's really big and really close, maybe that gives EHT folks more things to look at. Yeah, I think that's where we're at. So thank you so much for having me.
Thanks for a wonderful and perfectly timed talk. Questions? Let's see.
I'm going to ask you a philosophical question. I hope it's okay, because I'm from the history and philosophy
I've been
group.
sitting with the philosophers the past couple days. So
a philosophy comment, okay?
Okay.
Peter can correct me. You say how to find supermassive black holes. You list a combination of interrelated scientific requirements whose dependence on each other secure reliability. Now, in philosophy of science, Nancy Cartwright, I don't know if you heard her name, in our field, she's very famous. She calls this the tangle of science. And you say we need spectral, high signal to noise ratios, high spatial resolution, large spatial coverage, and a bunch of other modeling. And these are all these requirements that depend on each other. Secure reliability. Now, what happens if one of these don't work and they all depend on each other?
Right, like in the sense
and then
where
you have robustness.
Right. So I guess is the question, like if we had, say, all of these, but we didn't have high spatial resolution, or if we had these but not high signal to noise, is that the sort of the crux of the question?
You see, it's all kind of, we don't search for truth. We search for reliability, and it's all interconnected. Now, if one thing does not work, you see, you say how to find supermassive black holes. Now, the thing is that some things cannot work as we expect them to work. And we check, it's all interrelated, and the problem is that we are all certain, okay, this will work, and this will work, and it's all interrelated into one big thing, and we check all of this, okay, this works, and this works, and this works.
Yeah, so this set of Right. So if, for example, we have some of these features, but we don't have all of them, the most significant impact that it has on the end result winds up being that it impacts our ability to to produce posteriors on the various parameter values. So, for example, there are a lot of folks who do stellar dynamical measurements of even galaxies that have black holes in them, but they don't have high spatial resolution, because if you're looking at relatively small black holes, you might not have enough spatial resolution to resolve the sphere of influence. But typically what happens there is that you might wind up with just sort of a limit, finding that the black hole must be smaller than some value. It really broadens the posteriors significantly. Or similarly, if you don't have significantly large spatial coverage, you start picking up degeneracies between sort of what you assume about the dark matter halo and the stellar components, which can also, in some cases, bias the black hole masses that you infer. So here we kind of have the best case scenario where we've, after decades of evolution in this field, we've really been trying to figure out exactly what we need. And in the best cases, we can sort of engineer the observations really well to achieve all of them. But there's certainly a lot of cases where some of these features are missing, and folks try to do the best that they can, and often what that ends up resulting in is a lack of detection or a very weak detection of an object.
Thanks. I think one of the things that you were pointing at, Galina, is the paradigm, right? Like, what happens if one of these things break? Do we still believe it? So one of the things that I'm really interested in for my very selfish paradigm is how your results fit in with the nanograv measurements. And so you said that you have a paper that you're going to submit soon, but that you were comparing I'm not really sure what nanograv number you were using to compare your results to. So I was hoping you could say a little bit more about that last bullet point.
Right. So yeah, hopefully the paper is like on archive. I'm basically waiting on like last rounds of edits from folks. And then as soon as that's done, it's, submitted. Yeah, so more or less, the argument that we make in the paper is a revision of a set of stellar mass measurements for galaxies in the massive survey, which is, the 100 most massive in our neighborhood. So basically that allows us to constrain what the stellar mass function above, say, 10 to the 11.5 solar masses, what that looks like. At least very close to z equals 0. I think the most distant galaxy we have is like 0.02 or something like that. So the claim then would be, if we have an improved mass function for the galaxies, we can infer what sort of black hole mass function pops up. If you make some assumptions about those, some of those being binaries or having been binaries in the past, then you can start connecting that to something like a characteristic strain that you might expect. So there we end up finding that, if we take some kind of big assumptions, but hopefully relatively safe assumptions, we can connect basically to the strain value. I think nanograv's strain value is like 2.4 times 10 to the minus 15. And we can get basically like 2.2 without really trying to like do anything. Just fairly hands-off, just get 2.2 from our data.
Awesome, thank you.
All right, let's take one more question. Sorry to fool you, I'm heading to Antonio.
Hi, it's great talk. I was wondering, for the image, the slide that you were showing, the JWST, the rings where you were taking the measurement, coming from the Bridging Scales workshop and understanding how the accretion, can be as small as like some of this like GRMHT simulation accretion measurement is below like 1 parsec, and I'm not an observer, so I cannot do a mental translation of how far you're probing I guess you're using. How far is this from the center, I guess?
Right.
In terms of parsecs.
Right. So in this image, so these two rings are unrelated to our observations, but this is basically the region that's showing up in this old spectrum. In our observations, we basically have this large image where we have 0.05 by 0.05 arcsecond spaxels, and those spaxels extend all the way down to the center. So, nominally the spatial resolution that we get down to is about 0.05 arcseconds from the center, which is roughly 4.5 parsecs. So we probably won't be able to see things that are on like the parsec or subparsec scale, but maybe if there are indications at that scale that are loud enough, it'll do something to the central pixel, but it would be also kind of hard to tell if that's, real or if it's noise at that point. So I don't know that we'd be down to that scale of subparsec, but we're going to be as close to subparsec as you can get without being subparsec. So that's kind of nice. Yeah.
All right, let's thank our speaker one more time. The final speaker of this conference is Hong Liu. He is a professor of theoretical physics at MIT. and he studies the quantum nature of black holes using the framework of string theory. Today he'll be telling us about Towards Stringy Horizons. Whenever you're ready, please take it away.
Okay. Yeah. Thanks a lot for the invitation. As the last speaker of this conference, I think I can say with full credibility that this has been a wonderful conference, and with fascinating talks in many different areas. And so I think we should all thank organizers for such a wonderful job. And also the conference has been very smoothly run, so we should also thank the organizing staffs for a wonderful job. So we should give them a big applause. So that also released lots of pressure on myself. Even if I give a terrible talk, I will not drag the level of this conference much. So we all know that in semi-classical gravity, even horizon is a boundary beyond which events cannot reach a asymptotic observer. Okay, so this is a statement about the causal structure of your space-time. And of course, this is fundamental to the definition of a black hole. And the horizon also plays central role in black hole thermodynamics, say Hawking radiation, black hole entropy, and also connects to quantum chaos, etc. But it's widely believed that Einstein gravity is not fundamental, but actually the low energy limits of something more fundamental. Okay, and such as say a string theory. So this is my best art presentation of a string. So this is a closed string, and so a string has a typical length scale which we call LS. So when you look at the length scale much larger than the size of a string, and then essentially the string just looks like a point particle. You cannot resolve it, and then we just recover the Einstein gravity plus matter. Okay, so mathematically we can also say we can also just keep your the scale you are interested in fixed, and then just take the LS go to zero limit. Okay, so we say the Einstein gravity comes from the LS goes to zero limit, say, of string theory. And when we say we have a finite string length, and then we say we are in the stringy region. Okay. Then the obvious question is that in the stringy regime, do the familiar geometric concept in general relativity still apply? Okay. For example, can we define a black hole? Can we still define even the horizon, etc., as we did, say, in GR? Okay. So if we understand such kind of differences, then that will provide possible clues for observation, consequences, say for string theory. Okay, maybe black hole can be used as a magnification lens for stringy effect. Then maybe we can use black hole to measure, to find clues to string theory. But still, many elementary questions not understood. Okay, for example, how do we actually define the causal structure in string theory, say in this finite regime of a finite string length? And to talk about the causal structure, you actually need to talk about, say, a sub-region. Say, if you you have to define things to be causally connected or disconnected. How do we define a sub-region, and then how do we define black hole or even horizon in string theory? So it turns out that this has been very difficult questions in string theory, and both due to, say, just in string theory to study black holes is really technically very complicated. But there's also fundamental conceptual difficulties in using string theory to study these questions. It's because string theory, as is currently formulated, is mostly a scheme to calculate scattering amplitude. So when you calculate scattering amplitude, you only need to specify your initial state and the final state, so at the far past and far infinity. And then such a formulation is not a good way to probe the interior of your space-time, which all these questions are concerned about. Okay. So that's why actually using traditional framework, we actually there's a fundamental barrier. Okay. So this then takes us to the ADS-AFT duality. So whenever everything fails, we go to ADS-AFT duality. So you have seen this mentioned in many different circumstances. And I was not originally to use this figure, but turns out that this has been used several times. So I thought I would use it so that I don't have to explain it anymore. And so you have string theory living in the bulk of the anti-de Sitter space-time, and then which turns out to be equivalent to a conformal field theory living on its boundary. Okay. So this conformal field, depends on what is the string theory here. Then you have a different CFT. And for our purpose, we only need to know that the CFT, say, have two important parameters. Say, one is I call n, is the number of field degrees freedom, say, over the CFT. And another is what I call lambda, is the coupling for the CFT. Okay. And it turns out the semi-classical regime, say, if you consider semi-classical gravity in anti-de Sitter space-time, that's corresponding to the CFT in the following limit, which you take the number of degrees freedom to be very large and go into the infinite coupling limit. Okay, so that gives you the semi-classical regime. So now if we want to go to string theory regime, and then you take n go to infinity, and then you take lambda to be finite. So in both cases, so in this talk, I always take n go to infinity. So what this n go to infinity controls is essentially the quantum gravitational fluctuation of this gravity theory. So since we are interested in the effect of Stringy effect, so for our purpose, we can just suppress the quantum gravitational fluctuations, of course, by its own interesting questions. Okay. And so now let's consider, say, in the semi-classical gravity regime corresponding to CFT with n go to infinity and lambda go to infinity. And then we can consider a black hole in ADS. Okay? So now in this regime, it's well known that the black hole in ADS is described by so-called the two copies of the CFT in the thermal field double state. So the reason you have two copies of the CFT is that as you know, for black hole, a fully extended Schwarzschild black hole, you actually have two asymptotic boundaries. So there's a CFT on each boundary. So on the left boundary, you have the CFT L, and on the right boundary, you have CFT R. And in the boundary, and these two CFT, they are entangled in the so-called thermal field double state. Okay. So if you don't know thermal field double state, it doesn't matter, and you only need to know this is the can be used as a Lorentzian description of a thermal state. Okay. And so this duality is well understood in this limit with many consistency checks. But now to understand stringy black hole, then we can say, let's just consider these two copies of CFT in the thermal field double state. Let's just consider the finite lambda. Okay, because finite lambda then corresponding to you have in the stringy regime. And then you can say R, then how do we, whether there's still a black hole in the gravity side, and if yes, whether we can define the stringy horizon. Okay. And this sounds like a wonderful idea, but this is actually a rather trivial idea, which of course was people immediately came up with this kind of idea immediately after the discovery of the ADS-CFT duality. But you haven't seen any actually any paper claiming they have fully described the stringy black hole or stringy horizon. It's because there's a big catch. Okay, and the catch is that this equivalence between string theory and the CFT, they differ by one dimension. Okay, so string theories in D+1 dimension have one higher dimension than the CFT. CFT living on its boundary. But in order to understand all these questions about black holes, then we need to understand the causal structure, general subregions, and even the horizon, how to describe those concepts in string theory. And that means you have to be able to describe those concepts in d+1 dimensional space-time using this d-dimensional theory. Okay? And that's actually a very difficult question. So in other words, we need a precise understanding how the box space-time and associated geometric concept emerge from this lower dimensional boundary system. Okay, so, and that's a highly non-trivial question. And so normally when we think about, say, emergence of space-time, we normally have in mind you have a metric, and then you consider the action for the metric and the matter fields on this metric, and then you can describe the space-time and all the physics in this space-time. Okay. And so there have been many attempts to understand the emergence of the box space-time from this perspective. Okay. But this has been turned out to be very difficult. Okay. And so during the last few years, with my former student, Sam Leuthauser, who is now a postdoc at Princeton, we have developed a new framework for understanding this emergence of space and time. And yes, actually, I taught aspect of it 2 years ago at this PHI conference.
Sorry, is the ultimate goal to get alpha prime corrections to the bulk ADS black hole metric? Like to get some smoothing out of the singularity?
Yeah, you want to, yeah. So from this point of view, indeed, from this point of view, you say, in the GR, you have a metric. And then if we understand how to describe this metric, you need a CFT. And then we go to finite lambda, then we can understand the alpha prime corrections to the metric, etc. Yeah, but this approach has been very difficult, both technical difficult and conceptual difficult. We have not made much progress on it. So now I will describe a different approach. Yeah, but that's a perturbative alpha prime correction still using the geometric concept, and then you don't probe the question how the string theory, whether the string theory will fundamentally change the geometric concept.
Yeah, you would get alpha prime order the fourth terms in the action.
Yeah, that's right. Yeah, because we want to see whether the stringy effect creates any conceptually different way to think about geometry. Okay, good. So now we have developed. We develop an alternative framework for understanding this question. And so the basic idea is the following. So this is what we call the sub-region sub-algebra duality. So the basic idea is the following. So first, in the semi-classical limit, which is the limit we understand for the gravity side, we claim there's a duality which you can associate any Bach sub-region with a sub-algebra in the boundary theory. So the boundary theory is a CFT, is a quantum mechanical system, and you can talk about the operator algebras in this quantum mechanical system. And that operator algebra have many different sub-algebras. So it turns out we claim there's one-to-one correspondence between these Bach sub-regions and the boundary sub-algebras. Okay? So the geometric properties of this sub-region will translate into algebraic properties of this sub-algebra. I will mention some simple aspects you will see. So for example, let's consider ADS. So let's consider you have three sub-regions, O1, O2, and O3. Okay? So for example, O1, and then is dual to some type 3-1 von Neumann algebra, which I call A1 on the boundary. So forget about this. If you're not familiar with these words, type 3-1 von Neumann sub-algebra, don't worry about it. So this is just some sub-algebra on the boundary. So boundary is a quantum mechanical system, and we have operator algebras, we have some sub-algebras. Okay. And turns out that this A1 can be argued to capture all the Bach physical operations in O1. Okay, so in O1, say you have a gravitational theory in O1, you can imagine you can perform, say, do some measurement, do some experiment within O1, And the claim is that all such kind of quantum operations you can perform in O1 is captured in this algebra, okay, on the boundary. And then the claim is that if you have the collection of all such algebras, and then you can actually fully recover all the physics of the Bach system. Okay, so this is a different perspective than thinking about, say, you have a metric and you have an action of that based on that metric, etc. So you really understand the algebra associated with each subregion. So let me give you some very simple, intuitive example how the properties of this O1 is captured by these algebras. Say, for example, this O1 is a subset of O2. And so this is simply reflected, the algebra A1 would be a subset of the A2 corresponding to the O2. Okay? And for example, the O1 and O3 here, they are space-like separated in the Bach. And so this is reflect the Bach causal structure. And then this is reflected in the boundary as that the algebra corresponding to A1, A1 for O1 and A3 for O3, they commute. Okay, they commute. So from this kind of commutation structure, you can actually deduce the causal structure in the Bach. And also, of course, in the Bach is a quantum theory. This O1 is entangled with the rest of the degree of freedom in this Bach system. And that turned out to be encoded in this type 1 structure of A1. So that's where this type 3-1 structure is important. Okay. Anyway, so essentially, all the Bach physics can in principle be captured by these relations or by the algebras, all the relations between these algebras. Okay, so philosophically, this sub-algebra, sub-region duality may be considered as a vast generalization of so-called the Gelfand duality in mathematics. So the Gelfand duality is the basic idea. So if you want to mathematically describe a space, okay, rather than assign the geometry to this space, you consider all possible functions you can define on this space. And you study the algebra of those functions. And it turns out that the algebra of those functions then capture all the geometric information of this space. Okay, so this is called the Gelfand duality. And here we are essentially saying the same thing. So each subregion in the Bach are described by the collections of the algebras in the boundary theory. And if you know this algebra, then you can capture all the geometry in the Bach. Not only that, but here we also capture the quantum operations you can perform in the Bach. Okay. Anyway.
Subregions, you really are taking the n goes to infinity limit, right? If you have finite n, these bulk regions will be subject to fluctuation.
Yeah. That's why I suppress the quantum fluctuations. Right. Yeah.
And all of these bulk regions are also boundary anchored and are Lorentzian.
No. They're not necessarily boundary anchored. No, they're not necessarily boundary anchored. They can be just Bach regions, any Bach regions. Yeah. So the reason that I suppress the quantum gravitational fluctuation here. Here I'm interested in the Stringy effect. Good. So the power of this approach is now if I consider the corresponding collection of boundary algebras, say which I already developed in the infinite lambda, which is corresponding to the classical gravity, and now I can just make the coupling to be at the finite. Okay, and then I go to the Bach Stringy region. Then I can just by studying the relation of those algebras at finite coupling, then I can try to deduce now the Stringy physics in the Bach. Yes?
Since the metric undergoes fluctuations and so on, it's hard to give a precise, exact description of a subregion, right? So
yeah.
In the end, is it just defined as the image of the subalgebra, or?
So the quantum fluctuation indeed will happen when you include the quantum fluctuation. But here I'm just asking the Stringy effect. So I suppress the quantum gravitational fluctuations by taking the larger limit. Yeah, so let's first try to understand the Stringy effect, and then we can relax that to include the quantum gravitational effect. Yeah. Okay, good. So this by studying those collections of the algebras, now we can, in principle, try to understand the box stringy space-time, including this causal structure. Okay. So, and then we may be able to define stringy horizons and black holes, etc. So now, today I will describe a modest progress in this direction by discuss a scheme that we can diagnose the existence of an even horizon in the stringy regime. Okay, we can consider the boundary dual to a string theory in the bulk. We can say, does this theory have a horizon or not? Okay, we can give a diagnosis. And so this is the recent, based on work to appear with Elliot Gasto, who is a math student at Caltech. Yeah. Mm-hmm. Good. So before tell you the scheme, so let me just give you some simple examples of the sub-region algebra duality, so to give you some intuitions. So first, if you have the full ADS spark, say in the vacuum state, okay, then that's just dual to the full boundary algebra. Of course, this is trivial. So now let's consider the following boundary algebra. Let's consider the algebra corresponding to the operators within a time band between minus T0 and T0 on the boundary. Okay? So you can ask, what does this algebra corresponding to in the bulk? So it turns out that this algebra corresponding to this wedge region in the bulk. So you send the light ray from T0 and minus T0, then they will join at some point in the bulk, and then the region between the joining and the boundary is this wedge region. And 3D picture would be like that. Okay, and so this A region would be the bulk region which dual to this boundary algebra for this time band. And now you can also ask, what is the algebra describe the complement of this A in the bulk, this region B? Okay. And now this you can now easily understand using the commutator structure, because from the bulk causal structure B, any operations in B will commute with those in A. And then that means that B is dual to the commutant of this Mi, so-called Mi prime. The commutant is defined to be all the operators do commute with this Mi in your CFT. Okay. And so now you can, so now interesting thing is that if you take this take this time band to be larger and larger, and eventually this A will cover the full Cauchy slice in the bulk, and then B will become empty for sufficiently large T0. Okay, so now then this Mi time band will equal to the full algebra. So that happens, say, when T0 is sufficiently large, and then you will cover the full Cauchy slice, and then B will become empty. Okay. So now let's contrast what happens in the black hole space-time. So in the black hole space-time, so let's consider time, so you have CFT left on the right boundary and the CFT right on the right boundary, and then I separate this into 4 regions. So then you can say, so you can establish that the bulk region R, which is outside the horizon, is actually dual to the full operator algebra for the right CFT. Okay? So the right CFT, the algebra is dual to the things in this right region. And now again, let's consider this time band in the right CFT between some minus T0 and T0. And turns out that is dual to now this wedge. Again, you send the right net rays from T0 and the minus T0 into the bulk, and then this wedge region then corresponding to the bulk region dual to this Mi. Okay. And now you can again ask, what is the complement of this A in the bulk? And so this is this big, this big region including L. But also including this B, which is the complement of A, which lies in the right region. Okay. So using the algebraic language, we say B is the intersection of the commutant of this Mi with the MR. Yeah, because the MR covers this right region. Okay, so this intersection of the right algebra with the commutant of A, then that gives you this B region. Okay, which is nice in this right region, but the complement to A. And now the key observation is that the existence of the horizon we can translate into algebraic language as that B, so here is a geometric language. The existence of the horizon is that B is non-empty for any T0. So no matter how large the time band you make, there's also a non-empty B here. Okay? And so that means that algebraically we can now translate it into algebraic language is that the commutant of this time band and the intersect with this right algebra is non-empty for any T0. Okay, you can make your time band as large as you want, and the commutant is never 0. Okay? And now, so this should be contrast to the situation as I described earlier to just empty A's without a horizon. When this time band becomes sufficiently large, then you will cover, the A will cover the full Cauchy slice, and then the commutant will become trivial. Okay. And now we can just use this idea, and now we have an algebraic formulation of the existence of a horizon. And this algebraic formulation now does not depend on geometry. And now you can just apply it to finite lambda. Okay, so the idea is extremely simple. So we can say, now consider the Lagrangian limit of 2 copies of CFT in the thermal field double state. And now we consider the right algebra. And now let's consider the operator algebra for the time band. And then when we say the system has a non-trivial bifurcating horizon, if this the intersection of the commutant with the right algebra is non-empty for any T0, for any size of the time band. Okay. And you can also generalize this idea. Here I talk about the bifurcating horizon for a simple Schwarzschild black hole, for internal Schwarzschild black hole. You can also define for the future and the past horizons, and for single-sided, for the black hole come from the collapse. Gravitational collapse. Okay, so we are not describing. The idea is similar.
This can never happen if you don't have an horizon in some other type of geometry.
Yeah. So now you have very simple algebraic criterion. We can just try to calculate it. Okay, it turns out that this is something actually can be calculable. Okay, in the Lagrangian limit, it's actually pretty simple to calculate. So in the Lagrangian limit, because the boundary algebra is essentially just determined by 2-point function of the operators. And the 2-point function are captured essentially by this so-called spectral function. It's the look at the commutator of 2 operators. Say, for example, this is a thermal field double state, and then this defines your spectral function, and then you can also go to the Fourier transform. So here I suppress the spatial directions because they are not important. Okay, so now to find this algebraic object for this time band, so it turns out you only need to solve the following question. You find the function of GT such that the convolution of this GT with this spectral function has no support in this time band. Okay, and then that gives you the commutants of this algebra. So this makes sense because the MI corresponding to the operators inside this time band, and we just need to find things outside the time band. Okay, and so now we translate this question into a calculus question. Okay, now you can just solve it. Okay, it turns out that actually there's a big and in many cases, this can be determined without knowing the details of behavior of this rho. You only need to know the qualitative behavior of this rho omega.
But actually, computing rho in practice is quite difficult.
Right. Yeah. Good. Yeah. Right. Yeah. So calculating the rho omega and the rho t is often very, very difficult. But the key is that in many cases, this can be decided by the qualitative behavior of omega. You don't need to know its explicit behavior. And it turns out that this is also related to some very deep mathematics and related to the problem in harmonic analysis called the gap and the type problems. And for example, these are some books which describe this kind of problems, which is also called the uncertainty principle in harmonic analysis. Anyway, so there's a rich mathematical literature on the same kind of question. Anyway, so now let me just very quickly tell you a couple of examples. Thank you. Let me just very quickly tell you a couple of examples. So this does have predictive power. So for example, let's consider the encoded super Yang-Mills theory, which is dual to type 2B string theory in ADS5. And then let's look at this at sufficiently low temperature at finite coupling below the Hawking page temperature. And then you can, in this case, you can show that the spectral function actually have a discrete spectrum with equal spacing 1, say in some unit, okay? And then in this case, just based on that it has a discrete spectrum with equal spacing, you can show that this object exists only for T0 smaller than pi. And for T0 greater than pi, and then this becomes empty. Okay, so that tells you there's no horizon. Okay, and this is consistent with our expectation on the gravity side. Say in the strong coupling, when it's due to the classical gravity, we know that this is due to the thermal ADS. Essentially, you just have two copies of empty ADS which are entangled. Okay, so in this case, there's no horizon, and so it's consistent. But now we are saying this picture can actually be extended to the stringy region. Okay. And another simple example is that suppose your rho omega spectral function has a continuous spectrum. Okay, the earlier example is a discrete, but only compactly supported. Okay, only in the finite region in the omega axis. And in this case, you find actually this object does not exist for any values of T0. Okay, so the horizon is also, of course, is also empty. And actually, there's a nice example for this. So this is so-called the LP model, which introduced by Izuka, Okuda, and Polchinski. And they use this model try to model the black hole system, okay, using some simple quantum mechanical system. And so this is, again, I will not go into details of this model, but the key feature of this model is that if you look at the spectral function, it's only supported in the finite region in the omega axis, so only in this red region. And so here we can immediately deduce that for this ILP model, there's no Bach horizon. Okay, but now let's consider the case which this omega have a complete spectrum. Means that it not only have a continuous spectrum, but actually supported on the full frequency axis. So in this case, you can show that this is non-empty for any T0 greater than 0. Okay, so in this case, then you have a horizon. And so this example is equal to super-Yang-Mills series with gauge group, at the finite coupling at sufficiently high temperature. So this gives you in this criterion, the string theory due to equal to super-Yang-Mills series at the finite coupling will have a stringy horizon. Okay. So very quickly, let me just finally mention. So it's now very natural. You can define a parameter T corresponding to the maximal size of the time band that this quantity is non-empty. Okay. So that means if the T0 smaller than this value, this is non-empty, but when T0 greater than this value, become empty. So in the compact spectrum, the T will be 0 because there's no T0, which is this is non-empty. And for the complete spectrum, this is T equal to infinity. T equal to infinity corresponding to the criterion which we have a horizon. And then for the equal space spectrum, and then we have something like this. Okay. And so intuitively, this parameter corresponding to the following. So consider general asymptotic ADS geometry, and then you can just send the light rays from the boundary to the bulk. Okay? And now imagine this bulk does not have a horizon, has the most central point. And then you can take this central point and send the light ray to the boundary, and then you can ask, what is the span of this size on the boundary when I send the light ray like this? And that's precisely this T. Okay. So essentially you have a larger T, and then you can probe deeper in ADS. So that's why we call this, Anyway, the T equal to 0, which corresponding to the radial direction is microscopic. Okay, so I think I'm running out of time. Sorry for being late. So I will just just conclude with here. Thank you.
All right. Thank you for a fascinating talk. We'll take one question.
Okay, thanks. I'm sorry if it's one question is a technical one. So is it true then if you have like a double scale limit of a finite support matrix model, then that will have a bulk horizon?
Sorry, say it again. You say double
Well,
scale?
it seems like the problem was that the spectral support was finite. So if you have a matrix model and you want to produce something that has an unbounded spectral support, you take this double scaling limit.
Yeah.
So will you always then get a bulk horizon?
Yeah, so yeah, it depends on, yeah, if you have a complete spectrum, and then from this criterion, you always have a
yeah, so my question is that the complete spectrum, is it guaranteed by taking the double scaling limit?
And not necessarily. Yeah, I think not necessarily. Yeah, the complete spectrum depends on the dynamics. Yeah.
Okay, let's thank our speaker one last time. I now hand off to Peter Galison, the director of the BHI, for final closing remarks.
What a pleasure it has been to see all these talks over the last 2.5 days. It's an extraordinary wealth of new research and interdisciplinary discussion that cuts across observation and theory, philosophy, social sciences even. And I think that that's been a mark of a field that is in an enormous flowering period. You know, as I think back across the history of the discussion of black holes, it occurred to me to make a comparison, just as a way of thinking about these things, with the development of quantum mechanics and relativity early in the 20th century. You know, if you think about the fact that the electron was discovered in 1897, Einstein's special theory of relativity is 1905, general relativity, the old quantum theory in 1912-13, general relativity 1915, 1916, where we have and then non-relativistic quantum mechanics in 1927. In 30 years, you go from the discovery of the electron to having an account by 1927 that included the electron's charge and mass and spin, its integration into calculations of scattering and the debates about the nature of physical law, determinism, probability. So much was compressed into those 30 years. And in a way, what we've experienced, I mean, collectively, not just those here, with black holes, they have, in certain sense, their origin with Schwarzschild and Einstein in 1915, 1916. Some of those same developments spread over 110 years and not over yet. We are not at the phase that non-relativistic quantum mechanics was in 1926, 27. And that's not because of a lack of effort or skill or anything else. It has to do with the scope of ambition of this. If you say the electron of the 1910s and 20s is the black hole of our moment now, that discovery, even the demonstration that black holes existed, you have the first experiment, observational development in Cygnus X1 in the 1960s. Hawking and Kip Thorne could make a bet in 1975 about that. And the larger demonstration of the existence of black holes, there are many people who have felt like you could name various places, but really it goes from Cygnus X1 through the work of LIGO and Gaz Gensel and the Event Horizon Telescope, in all sorts of ways to demonstrate the existence of black holes. And we still don't have a direct measure of spin, which was the measure of spin, and spin was off there for the electron in 1920, Stern-Gerlach, or 1925, Goudsmit and Uhlenbeck. So you've got, I think sometimes it's hard to see the revolutionary moment that we're in because it's distended in time over a much larger period than would have been present in the discussions of the 1910s and 20s when special relativity and non-relativistic quantum mechanics were stunning the world. Of course, black holes appeal to everybody. Every 5-year-old likes black holes. But the depth of understanding of the nature of physical laws, of the questions of determinism. Einstein once said, was criticized that relativity was not intuitive, and he said, intuition is historical. It wasn't intuitive that objects travel in straight lines forever at a constant velocity. That was a hard-won victory of the entire early modern period of physics. Galileo didn't think objects traveled in straight lines. He thought that the natural motion of objects was circular. So that was a battle to win that. And Einstein said, that continues. We're still trying to gain the intuitive understanding. We had lots of discussions after Bob Wald's talk about, what is this region for in his chart? How do we understand being behind, if that's even a concept, the inner horizon? But these concepts are deep, and it's going to be a while yet before we learn many of the fundamental questions about black holes. And that's good, not bad. That's not a criticism. It's a hope that the black holes are the gift that keeps on giving, both to our insights into the nature of space and time, and of determinism and the nature of physical law, and also helps us to understand the structure of galaxies. Galaxies. Kant proposed galaxies in 1755 as a collection of stars, and it's only recently that we come to understand that every galaxy is co-evolving with a giant black hole at its center. These are hundreds of years projects that are unfolding still in exciting ways. There are also parallels between these two epochs, the epoch of the electron and the epoch of the black hole, in the kinds of techniques that we use. Spectra played a formative role in Bohr generating his early theory of the atom. It played a constant role throughout the development, even into quantum electrodynamics, and in the development of spectra in other senses with excited states of nucleons and so on, in the development of the quark model and beyond. And spectra will play a role, as we've heard this morning, and in many other talks throughout the conference, in our understanding of black holes and their dynamics in galaxies. The interferometer may be the most important instrument in the history of modern physics. Michelson held the first spectrometer, the first of his interferometers in his hand. It's about this big. And we're now thinking about not only the interferometric measurements that constitute the Event Horizon telescopes and its extension and development and articulation in terrestrial form, but in concert with space VLBI. And then Lisa is thinking of a 2.5 million kilometer equilateral triangle in space. So this instrument has saturated the history of both the electron, special relativity, and the development of black holes. And scattering. Scattering is crucial for the development and understanding of the electron epoch, as it is in the reformulation and novel approaches to how we think about scattering in the epoch of black holes. For all these reasons and many more, I think we're participating in a revolution in the nature of physics, but it's one that's unfolding at a pace that's not as visible as it might have been in 1905 or 1919 when Eddington saw the first bending of starlight. It's not that sudden. It's spread out, but it's exciting and deep and